Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, we've got a great topic for you today, one that I think a lot of you control engineers can really use. Here it is. Control a VFD using its built-in Modbus RTU port. Now, one of the great things about Modbus is it is everywhere. So just about every industrial device, even really inexpensive ones, support Modbus. And the form of Modbus that they support most often is Modbus RTU. And that's absolutely true with most variable frequency drives. Even the least expensive variable frequency drives almost always include Modbus RTU. And if you take advantage of that free capability, it's built into the drive, it's built into the Horner OCS all-in-one controller, then you can add great functionality to your application really at no extra hardware cost. Just the cost of you actually implementing the feature, which can give you a lot of benefits that we're going to talk about today. So without further ado, let's dive right into the topic. Okay, we're going to start with a quick review of Modbus RTU to get you more familiar with that particular protocol. We're going to talk a little bit about the benefits of using Modbus RTU for VFD control, because there are a variety of different options. Some other protocols are probably better in other situations, but there are so many situations where Modbus is a great option that we want to share that with you. And then we're going to walk you through the integration process. So when you're actually getting your OCS all-in-one controller to talk to the drive and control the drive, what's the process of getting those two integrated together in your system? So we'll talk in detail about the wiring that you're going to need to do. It's pretty straightforward, but we want to make sure those details are shared. We're going to talk about identifying the key VFD parameters that you'll need to adjust to get communications going. Now keep in mind, the particular drive you may be using is going to have a unique parameter map. So I'm going to be talking in general about the type of parameters that need to be adjusted, and then I'll be giving as an example specifically a drive from Invertech, which is a really nice product, which I'll be using in my demonstration. And then I'll be talking about what do you need to do to set up the VFD, okay? What parameters do you need to adjust before communications can occur? And then we're going to spend quite a bit of time on showing you how to configure the OCS all-in-one controller to communicate with the drive over RTU Modbus. And of course, we're going to have plenty of demonstrations throughout, not only configuration in the Cscape 10 software, but also bench demos as well. All right, let's go ahead and get going. Okay, so we're going to start with what is Modbus. So Modbus is the most common industrial protocol for interfacing industrial devices. It's not the fastest, it's not the slowest, it's not the most advanced, but it's the most common. It's been around a long time, and more devices in general support Modbus than really any other protocol. So it makes it kind of the common denominator on the factory floor. Now, Modbus has many forms. Okay, so this protocol can be used with different media in different applications. So Modbus TCP is Modbus protocol over Ethernet. Modbus ASCII is used in a lot of cases for Modbus communications over a radio. So maybe in a wastewater type application, or an application where you've got devices that are flung over a fairly wide geographic area, at least in a region, within a region, maybe within a municipality or something. You might use radios for communications, and you might use Modbus ASCII as the specific protocol in that case. And then you've got Modbus RTU, which we're talking about today, and that's using Modbus protocol serially over an RS-485 network. Okay, so that's what we're going to be talking about today. All right, now how does Modbus work? Modbus is a register-based or address-based protocol, so it's not an object-based protocol like a lot of the newer, more modern protocols, okay? But in the application we're talking about today, that's really not an issue. Even though it's register-based, it still works extremely well for interfacing with devices like drives. Okay, now Modbus registers, since it's a register-based protocol, are organized like a traditional PLC. So you have 4 different types of Modbus registers, okay? Starting with coils, which emulate digital output bits. You have inputs, which emulate digital input bits. You have input registers, which emulate analog inputs, in other words, read-only inputs. And then you have what's called holding registers, which emulate analog outputs or internal PLC registers, those sorts of things. And in a lot of the cases, a lot of drives are primarily based on holding registers from a Modbus perspective. So in the case of the Invertech drive, all the Modbus or all the drive parameters, I should say, everything you need to know, all the data you need to read or write, whether it's bit, word, or whatever, is all mapped to holding registers. So that's the particular case with Invertech, and it's also true of a lot of other drives as well. So again, 4 different types of Modbus registers. Now, how are those registers numbered? Okay, well, it really depends on the manufacturer as to how those are numbered. Now, officially, you have traditional 5-digit Modbus addresses. This is kind of the official way that Modbus is mapped. So you can see in each of the 4 different types of registers, you have 10,000 entries there. So 10,000 coils starting at number 1, 10,000 input bits starting at 10,001, 10,000 input registers starting at 30,001, 10,000 holding registers starting at 40,001. So this is the traditional type of Modbus numbering system where each memory type has its own unique numbering range. Now, another thing you'll find with some manufacturers when they give the addresses of their Modbus data is they'll just have a number from 1 to 10,000 for each of the 4 different types of registers. Okay, so they may specify, okay, it is input register number 1. Okay, or they may specify it's holding register number 1. Okay, so again, that's another way that some manufacturers address the 4 different types of address space, where each memory type is addressed starting at 1 instead of with its own unique number. Now, another approach that is taken by some manufacturers is they'll actually list an offset instead of an address number. Now, Modbus is a 1-based address number system, okay? But if you give an offset, then you're giving a number starting with 0. So for instance, if you're giving an offset to the first holding register, you would say, well, that's offset 0. And some places they'll actually list it in their documentation as address 0, but it's really, if it's the first entry for a particular section of Modbus registers, you know that's a dead giveaway that that's an offset and not actually a address number. Okay. Now, so that gives you an idea of the 4 different types of Modbus data that's available, all right, and how they may be numbered for the particular manufacturer that you're using, all right, and we'll talk a little bit when we get into the demonstration how Invertech chooses to number their particular holding registers in their case. Okay, but in addition to knowing the different types of registers, as well as, paying attention to how they're numbered, there is also something in Modbus called function codes. These are commands in the background, usually in the background, okay? In the case of the Horner OCS controller, which is going to act as the Modbus master, the OCS is executing these function codes to communicate with the drive, but you don't necessarily always need to know specifically which function code is being used. You just need to understand what function codes are there and which ones are supported by your particular drive. So you have function codes to read coils, to read inputs, to read holding registers, to read input registers. You also have different function codes for writing a single coil, for writing a single register, for writing multiple coils, and writing multiple registers. Okay, so those are the most common Modbus function codes. Now there are others, but I'm not going to cover all of those because frankly, these are the most common and these are the ones you probably need to know if you're just talking to a variable frequency drive. That's a little bit of background on Modbus, how it's organized, how it's numbered, what function codes are supported, and keep in mind what we're doing here is we're looking to control a drive over Modbus and also potentially read important status information from the drive as well. So what are some of the benefits of this? What are the benefits of using Modbus RTU to control a drive, as opposed maybe to hardwiring everything, where everything is hardwired from digital outputs or analog outputs or monitored using digital inputs or analog inputs with your PLC? What are the benefits of maybe using Modbus RTU instead? Well, first of all, with most drives, Modbus RTU support is included for free. So it's there on the drive. You're not paying anything extra for it. You might as well take advantage of it if it can give you some benefit. Now, what does that Modbus RTU provide you access to? Well, it gives you the ability to start and stop the drive, control the speed. It can allow you to monitor power and current data. All right. It allows you to read and write individual drive parameters if you need to do that on an occasional basis. It also gives you the ability to read faults as well as reset faults, which can be really valuable. Also, if you do some of these or all of these functions over Modbus, it's going to reduce the amount of PLC I/O that you need to allocate to the drive. Now, you may choose to have a mix and match where some functions of drive control are done using hard wiring from your PLC or your Horner OCS, and some functions are done over Modbus. So you can mix and match to a certain extent. But again, there's a lot of benefits to taking advantage of this free protocol that's built in. So if you've got a pretty inexpensive application, it's a pretty routine pump control application, why not take advantage? It's built in for free in the drive, it's built in for free in the Horner OCS controller. Okay, now let's talk about the wiring of RS-45, which is what is almost always used with Modbus on drives, at least when we're talking about Modbus RTU. Okay, so most manufacturers will recommend a twisted pair wire for communications, as well as an extra conductor that's used as a common reference. Okay, so I'm showing you there on the screen a twisted pair plus a common reference. Now, some manufacturers will list those two communications conductors as plus and minus. Some will label it as A and B. But the difference is, or the important information is, regardless of whether it's labeled plus and minus or A and B, you're going to wire straight through plus to plus and minus to minus, or A to A and B to B. All right, so that is the wiring, at least from the standpoint of the conductors for communications and the one for the common reference. Now, in addition to that, if you choose to use shielded wiring, and you don't have to use shielded wiring in all cases, if you do choose to use shielded wiring, then you should make sure that you connect the shield drain to earth ground, and most drive manufacturers will recommend that you do it away from the drive. So not inside the drive chassis. You wouldn't want to ground there. You'd want to ground at a good earth point that's not inside the drive, for instance. You're going to want to do it away from the drive. Now, whether you use shielded wiring or not, you're definitely going to need to have termination on both ends of your communications pair. Okay, now, depending on the wiring you use, that could mean 100 ohm wiring, 100 ohm resistors, I should say, or it might mean 120 ohm resistors. All right, but in most cases, I think 100 ohms will work just fine. All right, but again, you're going to need it on both ends of the network. So if all you have is the OCS or a PLC and your drive, and those are the only two devices on the network, that means each of them is on an end. That means you need termination on both ends. Now, in the case of the Horner OCS all-in-one controller, there is a system menu entry that allows you to enable termination. Okay, so you don't have to physically add a resistor on the OCS side, because you can just go into the system menu and turn that termination resistance on in the system menu, and it will automatically add internally to the OCS that 100 ohm resistor to the communications path on the OCS side. Now, on the drive side, in terms of adding termination, some drives you'll need to add a physical resistor. Other drives may have a setting or a switch that you can use for that as well. So you need to consult the particular settings on your drive. In the case of the Invertech drive, in my demonstration, I went ahead and added a physical resistor to that end of the network. Okay, now this is something that usually you don't need to worry about, and that is something called bias. So the only reason you would need to add bias to the system is if for some reason you're getting some stray bits or some stray communication errors that are occurring. So usually you don't need this, but in the case of the OCS, when you're using the OCS with a drive, if you decide you want to turn biasing on because you're getting some communication errors, you can again do that from the system menu to turn that on and off. Okay, so again, bias is something you usually don't need to add and you only need to add it at one location on the network. And in the case of the OCS, you can just turn that on if needed from the system menu, but normally I recommend you start with that off and only use it if you need to. Okay, so the next thing you're going to want to do when you're going to integrate a drive with a PLC or a drive with a Horner OCS is figure out how you want to break up the functionality. I talked earlier on an earlier slide that you could do everything over Modbus: start, stop, adjust speed, set acceleration, fault codes, fault resets. You can do everything over Modbus if you want, or it could be a mix and match of doing some things over a hardwire and some things over Modbus. So you just need to decide how you want to break up that functionality. Now, that's one of the areas you'll need to consult your drive documentation to see what control the drive manufacturer gives you over what is hardwired and what's Modbus controlled. Each drive is going to be a little bit different. Again, we really need to start accessing our drive Modbus documentation at this point in the integration process. Okay, so we're going to want to look at that documentation for Modbus and see, okay, what parameters are available over Modbus. You know, some drive manufacturers have hundreds and hundreds of parameters that are available, and most certainly you aren't going to need to access even a fraction of them, all right? So you're going to want to identify the ones that are important to you for your application. In general, most drive manufacturers are going to have something approximating a control word, okay, which will give you the ability to start and stop the drive, to clear faults, and those sorts of things. Some drive manufacturers may have individual bits to access over Modbus for doing that. So again, you need to consult your individual drive documentation. In the case of the Invertech, they do use a control word approach for starting and stopping and clearing faults and those sorts of things. Now, after you determine what functions are available over Modbus and the ones that you're interested in, you also need to pay attention to what is the address format that this manufacturer uses for Modbus. Now, let's take a look at this page from the Invertech documentation. Notice in that left-hand column, it lists register number starting with 1. Elsewhere in the documentation, it states for Invertech that everything is done using holding registers. So what that tells us in this case is that the Modbus registers are numbered from 1, so they're not offsets. If that first entry in the upper left-hand corner was 0, that would tell us, okay, that's an offset, not a register number, because Modbus registers are always 1-based. Okay, so what this tells us is that we're going to have to add a value of 40,000 to the register number to come up with the 5-digit Modbus address. Okay, and we'll review that when we get to the configuration in the Cscape software package for the Horner OCS. Okay, so after we've looked at the parameters, figured out what the format is, we're also going to want to take a look and see, okay, somewhere in the documentation, what Modbus function codes are supported. Or some drives will list all the Modbus function codes that are supported, and if only a couple are listed, then it may actually impact the configuration on the OCS side. But normally for most modern drives, that's typically something that you don't have to really worry about. You should check it to see what function codes are supported. You know, read holding registers, write holding registers, write multiple holding registers. If those are supported for most drives, you're in pretty good shape. You don't have to worry about it after that. Okay, now, once you've done that, you know, you've looked at the documentation for the drive and figured all that out, now it's really a matter of setting up the drive by adjusting a few parameters for Modbus control. So in the case of the Invertech, parameter number 12 is the one that you're going to need to adjust if you want to set Modbus as the primary command source. Okay, this is what's true in the Invertech drive. So in my case, I've decided to use set parameter 12 to a value of 3 in my demonstration. That means I'm going to control the drive over Modbus RTU, but I'm going to leave the acceleration and the deceleration to the parameters that are in the drive. If I was going to be actively changing acceleration and deceleration in my application, I probably would choose parameter 4 in the case of the Invertech drive, so I could adjust the XL and decel ramps over Modbus as well. Okay, so that was, in the case of Invertech, where I set my command source. Now, also in the case of Invertech, I can adjust parameter 15, okay, set its value to determine how I want to break up the control between the drive and hardwired I/O. And in my case, I just left it at the default of 0, so that effectively what that says is for the first digital input, DI1, in that left-hand side there, basically what that says is I'm going to have to make sure digital input 1 is on, okay, if I want the drive to be enabled so that I can start and stop it over Modbus, okay? So digital input 1 has to be on or passing power, okay? And then digital 2, 3, and 4, along with the 2 AIs, are going to be ignored from a control perspective. All my control commands are going to come over Modbus. Okay, so that's the second step there in the case of Invertech. And then the third step for your drive is going to be to set the Modbus address, the baud rate, etc., for communications over the serial port. Now, I like to leave these at default if I can. Okay, in the case of the Invertech, the default is address 1, baud rate of 115.2, and a timeout of 3 seconds. In other words, the drive will wait up to 3 seconds to be commanded, otherwise it'll flag a fault. All right, now, the only one that you would need to change would be the address if you have multiple drives on the same network, because they obviously can't all be at the same address. All right, so again, this is going to vary depending on the drive you have, but you need to set your command source. You need to potentially divvy up the control between hardwired I/O inputs as well as Modbus, and then you need to set the Modbus communication parameters. That's going to be pretty universal depending on your drive, but the parameter numbers, of course, are going to vary. Okay, next we're going to talk about configuring Cscape software to communicate with the drive. But instead of going through a bunch of slides that talks about, here's this dialogue and that dialogue, let's just dive right into the demonstration and fire up Cscape now. All right, let's take a look at our configuration for talking via RTU Modbus to, in this case, an Invertech variable frequency drive. Okay, so the first thing we're going to want to do is to configure the Modbus communications with the drive here in Cscape 10. So I'm going to go to the hardware configuration, okay, which I can find here under the home section. All right. I am currently, for this demo, I'm using a Micro OCS X7. Great controller for pump control type applications and other applications where you've got, simple applications with variable frequency drive control. Okay. And then the Modbus configuration, the Modbus serial or Modbus RTU configuration is found here under serial ports. So I'll go to config. All right. And then MJ2, in the case of the Micro OCS, is the RS485 port. That's the one I want. I'm talking RS485 Modbus RTU to the drive. And I select from this pull down list, I select Modbus Master from the list of available protocols. Okay, now there's 3 levels of configuration that we do when we're talking the OCS acting as a Modbus RTU master. All right, let's start on the network level. So this is where we configure the baud rate, parity, data bits, stop bits, etc. that we're going to use when we communicate with the drive. Now, I like to use the defaults here, the defaults for the drive. In this case, these are the default parameters for the Invertech drive. On the right-hand side here, I select Modbus RTU. And then down here under timeout, okay, the retries isn't quite as important, but under timeout, I like to make sure this is a pretty short number. So I've got it set to 1 second right now. The default is higher than that. So if I've got a direct connection, and especially if I'm only talking to one drive, there's really no reason for this timeout value to be high at all. So 1 second is about as long as I would ever want to make that. So that's what I've set it to here. Again, retries, you can set retries to any number between 0 and 255. That one's not really as important. Another important parameter to adjust is reacquire time. So the timeout is how long the OCS will wait for the drive to respond to any particular message. When it times out, it will retry the number of times that are specified here. And when the retries are exhausted, it will then wait until a reacquire time expires before it starts the whole process of trying over again. So keeping the timeout short and the reacquire time short is really what you should do if you're just talking to like one device or even a couple devices over a hardwired connection like we are here. Okay, finally here on this side of this update scan area, we're going to leave the update scan to automatic, and we're going to set the update interval to 0. So what that does is it basically tells the OCS to pull the slave as fast as you can. So again, automatic and update interval of 0, we're going to pull the slave as fast as we can. All right. And then finally down here, let's take a look at a couple other things. So there is an optional bit type variable that you can assign here under disable network. So what that will do effectively is it will give you a Modbus reset bit that will reset Modbus communications in the OCS master if you toggle this particular bit. Now, I always assign it. I don't know that I've ever had to use it, but if you ever had something weird going on with your network and you were having trouble communicating, after you had been communicating normally for a period of time, then it would be a useful bit to be able to toggle in an attempt to kind of reset things. And then finally, this is really valuable. This is the Modbus master status, which is a double integer type variable array with 4 consecutive 32-bit values. And I've assigned a variable called Modbus status, a 32-bit variable array with 4 members. And that's going to tell us everything about the communications. How fast are we polling the slaves? How many good messages are we getting? How many bad messages? How many corrupt messages? Those sorts of things. So that's very valuable. So I would suggest that you definitely take advantage of that. Okay, so this is the network level of configuration. Next, let's take a look at the device level. This is where we tell the OCS about the slave or slaves that we're going to be communicating with. I've already added my Invertec drive here, but let me show you how I configured it. All right, so you give it a convenient name. All right, I've just called it VFD. And this is where you put the Modbus slave address. Now, the default slave address for an Invertec drive and most drives is 1. If I had multiple drives, I would have multiple entries in my device configuration, and they would vary by their device ID at the very least. So if I had 3 identical Invertec drives, this configuration for the most part would be identical, but my IDs would vary by drive. And to change that ID in the drive, I would go into a specific drive parameter and adjust that. Okay, but in this case, I'm just leaving it at the default of 1 because I only have 1 drive. Now, this is where we set the Modbus addressing style, or at least the one that's the closest to what we're looking for any particular drive. Now, in the case of the Invertec, it uses exclusively holding registers. It doesn't use anything else, Modbus holding registers. And those have a typical Modbus 5-digit addressing style of 40,001, 40,002, 40,003, etc. Okay. In the Invertec documentation, it lists those holding registers as 1, 2, 3, 4, etc. So it uses the Modbus holding registers, but it doesn't use an offset, which is a 0-based number from the beginning of the memory location. It uses a 1-based address, but it doesn't start it at 40,001 in the documentation. It starts it at 1. So none of our options here are super close to that. Okay, if we were using an offset, we would use one of these generic decimal or generic hexadecimal choices because these are actual offsets. Okay, and the Invertec doesn't use an offset. We'd only use native addressing if another OCS was the slave that we were talking to, and obviously we're not doing that here, we're talking to a drive. We'd only use 6-digit addressing if it was Modbus TCP over Ethernet, and we were talking to some huge device that had 100,000 holding registers instead of 10,000 holding registers. So in this case, the closest approximation of the addressing we want to use is the default of 5-digit addressing. And if you're not sure exactly which one to use for your particular drive, use the 5-digit addressing. Okay, what else is left here? Well, this is very valuable if you have multiple drives on the same Modbus network. So let me give you an example. Let's say you have 3 drives. It's a triplex pump system, and at any given moment, one drive could be down for service. So you don't want to be sitting there trying to pull that drive that's down for service. So what you would do is, for each drive in your system, you would assign a disable bit, which when set would cause the OCS just to ignore that drive completely. So that's very valuable if you have multiple drives on the same network. So it's just a Boolean 1-bit variable. Okay, and then down here, we have more status, but this is Modbus status from a drive perspective. So if we attempt to access a illegal parameter from the drive or something like that, we'll get an error message that's Modbus related that we can look at for diagnostic purposes. And this is just two 16-bit words. So I've created an integer variable that is an array with two members. And I can monitor this to make sure everything's working properly. If it's working properly, these values will just be 0. If I have a problem, Modbus related with this slave, particularly generally means I've done something illegal and trying to read or write to it, then these values will be non-zero and I can then look that up. Okay, so that is the device level of configuration. And I just have one device in my example here. All right, now let's look at the third level, which is a scan list, which is the list of data that we're going to read and or write with the Modbus slave, which in our case, of course, is a variable frequency drive. Now, if I had no members of the scan list here, or no entries in the scan list, it would be blank and I'd have to hit add to start. But since I've already got entries in my scan list, let me just go ahead and go through those for you. Okay, so if we take a look here at the top, this is the device that the data that we're going to read or write is coming from. Now, in this case, I only have one drive that I'm talking to, so there's only one device to choose from. If I had multiple drives, they'd be listed here in a row because I would have added 3 devices, for instance, as an example, in my device list. All right, so this is the device I'm going to be reading or writing to. Now, this is the 5-digit Modbus address that I want to read or write, the starting address. So in this case, the Invertech has 2 registers right at the beginning of their Modbus map that I'm interested in. The control word is the first one, and the frequency set point is the second one. And these are both read-write values. Okay, and so I'm definitely interested in mapping those to my PLC variables. So I'm going to start at 40,001. And with a length of 2. Now, if I look at the Invertech documentation, it lists these in the Modbus documentation as register number 1 and 2. Remember, it's using one base addressing, but it kind of leaves off the 40,000 part. So I just have to add 40,000 to make this a true 5-digit Modbus reference and then add it in here. Okay, so here's my starting register. And here is my length of 2, because I'm getting 2 consecutive. Now, all my Modbus data with the drive is going to be mapped into this word type variable, because remember, we're only using holding registers with the Invertech drive, and holding registers are always word type. And I've created a long word type array where I can put all the Modbus data that is going to be read and or written. Okay, and then so in my program, in the OCS program, this is where I will find the holding register data to either read or write. Okay, now in this case, these 2 words are read-write data. So what that means is normally the OCS will be reading the data, but if we change it in our program, maybe change the speed or change the start or stop status or start or stop command, then that data will be written. Okay, so this is read-write data. All right, so that's the first 2 words that I am mapping with the drive. Now, one thing we always want to do when we're creating a Modbus scan list is we want to optimize that scan list so that we have the fewest number of entries possible. In other words, let's say we had 7 words of data we were interested in reading, and they were scattered among 20 consecutive Modbus holding registers. Well, instead of having individual pulled reads for those 7 different values, which takes a lot of time, frankly, it'd be much faster for us to have a single read that reads 20 consecutive values, and then in our program, we would just access the 7 that we're interested in and ignore the rest. So again, you want to optimize your Modbus scan list. Okay, the second entry in our Modbus scan list starts at 40,006, or in the Invertech documentation, they just show that as 6. And there are 3 consecutive words that I'm interested in, and this happens to be read-only data. This happens to be the drive status and error code, if we have one, that's the first word, the output motor frequency that's actually going on right now, and then the actual motor current. So I'm interested in all 3 of those pieces of information. So I'm specifying the starting Modbus 5-digit register here and the fact that there's 3 of them, and I'm mapping those into the same array, but this time instead of at the beginning, starting at 0, I've skipped the first 2 entries, which are already mapped, and I'm going to the third entry here, which is index of 2. And again, this is read-write data. Now the third entry in my list is also read-only data, but this is 5 words that starts at 40,020. So that's how I've chosen to map those here. All right. And this is a polled read. And again, I'm mapping this information into address or index 5, 6, and 7 in my Modbus data array. Okay, and these 5 words of data in the Invertech drive at least are the 2 values of my analog inputs, if I decide to use those on the drive, the speed reference value, in other words, the speed that the drive will move to the next time it runs. Basically, it's the speed that's been commanded. And then I've also got the DC bus voltage and the drive temperature. So I figured that could be useful information. So I went ahead and mapped those there. Okay, so that's my scan list that I've created for this particular example application. I've got 3 entries, which is pretty good. Now I could have done this a little differently. I could have just had 2 entries or even just 1 entry and said, start me at 40,001 and I'm gonna do 25 or 26, I guess 25 entries. I could have done that and just picked the particular data that I was interested in. So that was another approach I could have taken. It may have been a little more efficient, but I think as long as the poll time, when we monitor that at runtime, is relatively short, I don't think we're gonna worry about that too much. Okay, so this is my scan list that I've created, and that wraps up our Modbus master configuration. Okay, everything else I have in my application is really just ladder for manipulating monitoring status and manipulating the control word to tell the drive to start, stop, clear faults, etc. So up here, I have some ladder. This is a simple start-stop circuit where I have a start and stop push button that are just, touchscreen objects. I have a status bit that I'm reading from the drive, okay, to make sure the drive's ready. And then I'm creating a coil, which is run enable. So if I try and start the drive, the drive's ready, I start the drive, this run enable coil is going to turn on. And this run enable coil, I've mapped it over or copied it over to the first bit in the control word. So this is the first word of Modbus data. That's that read-write data with the drive. That's that first word there. So I am copying my run enable coil from my logic over to that bit. So when I start the drive up here, that turns on. When I stop the drive here, that turns off. Also, I have a fault reset push button, which is just a touch object on the screen, and that is mapped over to the third bit in the control word, because that's in the Invertech documentation, that's the bit that resets a fault. And then these other 3 bits that I have here are really just taking status, okay, from the third word in the Modbus data array and creating the first bit in that third word tells me if the drive is running or not. The next bit tells me if the drive is faulted. It's got a trip because of a fault. And then the 7th bit tells me that the drive is ready. So this is the status word here, VFD index of 2, which is the third word in the array, because array start at 0. And I've mapped these 3 useful pieces of information over to coils that I can then use on my screen. Okay, and then finally, I've taken from that third status word the fault code, which is in the upper byte, and I've moved it to a new variable in the lower byte. So instead of having it, as the upper byte, I need to move it to the lower byte of an integer variable. I've done that here so I can display the fault code and interpret it and those sorts of things. Now, I've also created a couple of screens, and I will give you more details on what these screens do when I give you the bench demo. So I've got one screen with a control panel, some information and fault code stuff, and then I've got another screen that tells me what's happening from a Modbus perspective. But I'll give you more details on those when we get to the bench demo next. Okay, now let's take a look at things on the bench. All right, so there is my X7 controller, all right, along with my drive and my motor. All right, so let's take a look at what's happening here on the screen. So as you can see in the upper left-hand corner, I've got a bit of a control dashboard, if you will, that shows me if the drive is ready. I can start and stop the drive. I've got push buttons for that. I can see if the motor is actually running. That's feedback coming from the drive itself. I can see what the speed reference currently is set to. That's on the left there. And then in the center, I have the ability to change that speed reference if I want to. And then on the lower right-hand side of the control panel there, you can see my actual motor speed is 0 because nothing's running. Bottom, I've got indication for faults. So if I have a fault condition happening, I'm going to have a red pilot light that turns on. I'll get a fault code along with a message that explains that fault and an ability to reset that fault with a reset push button. Upper right-hand pane, I've just got some drive information. What's the current? What's the drive temperature? What's the DC bus? And then I have diagnostic information on another screen that I've got RTU status. So let me switch to that screen. In the upper part there, that's where I'm utilizing that Modbus master status. Those 4 double words of information are at the top there. What's my pull time? Well, 40 milliseconds-ish, or maybe 50 milliseconds, depends, varies a little bit. But basically what that's saying is how quickly am I reading all the data from the drive, okay? And then under no response and bad response, I have 0. That means I'm communicating with the drive just fine. That's what I'm looking for. And good response, again, is climbing up. That really is what tells me that I'm talking to the drive properly, because that indicates good responses, which is what I want. I want that counting up pretty rapidly. And then bottom center in yellow there, that's the specific status words coming back from the drive in regards to Modbus. And those are both 0, which is what I want. And then in the lower part of the screen there, I've got my drive status control word, which I've just put there for informational purposes. All right, let's go ahead and run the drive. So I'll go back to the control screen. Okay, so you can see my drive is ready. All right, let's just go ahead and start it. Okay, so you can see my actual motor speed climbing up. All right, my drive current has increased above 0. Let's go ahead and speed the thing up a little bit. Okay, now we're up to 45 hertz. Up to 60 hertz. All right, so everything's working great, and I can go ahead and stop it from here as well. So you can see my actual motor speed going down to 0, and as soon as I stop the motor run, feedback will be set to 0. Okay, and if I change my motor speed reference, or my motor speed that I want to set to, you can see my speed reference go back down to 45, and of course, the next time the drive starts, if that speed doesn't change again, then we're going to be running up to 45 hertz. Okay, in this particular example, for the acceleration times and those sorts of things, those are going to be set in the drive itself. I could have set up the Invertech drive so that I can control the acceleration and decelerations from the PLC or from the OCS in this case, but I just went ahead and let those in the drive for demonstration purposes. All right, so that is a look at our VFD setup on the bench. Okay, the last thing I want to show you on the bench is where you can turn on termination and potentially bias in the OCS menu system. So this happens to be a micro OCS. So I'm going to push the upper right-hand corner here to pull up the system button, which I can then press to get the system menu. And then under serial ports is where I can set termination and potentially bias. Okay, so down here under MJ2 RS45 termination, I have it set to yes, and that's because the OCS is on one end of the RS45 network, so it needs to be terminated, so I just turn it on from the system menu. And I mentioned in the slides when I talked about wiring, bias should only be added if it's absolutely necessary because you're getting some errors on the communication line. I'm not having any errors whatsoever, so I'm going to leave that at no. Okay, so that's where you can adjust your termination and bias. Okay, we're done with our topic today, so this is where I remind you that we're here just about every Tuesday at 2 o'clock. If you watch live, we'd love to answer your questions from the chat section. If you're watching on replay, give us those questions and comments in the comment section. We're pretty good about getting back to those pretty quickly. Okay, we've got lots of classes planned for 2025, so check out the Horner training schedule on our website. Lots of ways to interact with Horner, not only on the website, but also the YouTube channel, where you'll find hundreds of videos like these, and you can also interact with us on LinkedIn. Next week, we've got a great topic. we're going to show you how to show live video on your Canvas all-in-one controller screen. Pretty intriguing application, and we're going to show it off next week. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose subscribe and choose notifications, you'll be notified every time we go live and every time we post a new video. Okay, so until next week when we talk about USB cameras and the Canvas all-in-one controller, let's all get out there and do us some good.